super excited to be here today. Thanks for coming to the session. So today, if I were going to take a poll around the room and ask how many people like waiting for their analytics jobs to run, I'd be willing to bet nobody actually likes that, except this one gentleman here. But I would say most people would not like to, sit there and wait for the analytics jobs to run. That's not the favorite part of their day. So today I'm going to talk to you about how to use concurrency in order to get better performance on your Spark and Hadoop jobs when you use a cloud storage. So my name is Stephen Wu. Happy to talk to you guys today about this topic. A little bit about me. I am a program manager at Microsoft. What I focus on is performance and benchmarking for Azure Data Lake. And I do a lot of performance tuning for Spark and Hadoop workloads with our customers. So this is a common topic that I get a lot. So I wanted to make sure I told the community more about this. OK, so jumping in, the agenda for today is we're going to talk about some key concepts so that we can level set everybody. And then we'll go into the general guidance for cloud architectures. So we'll dive a little bit deeper. And then we'll go down to actually running Apache Spark and Apache Hive jobs and making sure that we can do good tuning there in the cloud. And then if we have some time left, we'll do some Q&A, and I'll be happy to answer any questions at that time. So let's just start off at the very top here. Why do we even use Spark and Hadoop clusters in the cloud? So some very big topics here. Cloud elasticity, right? Being able to scale from 0 to 100 in terms of the amount of storage and the amount of compute capabilities you have. Amazing, right? Second, being able to scale cloud compute and storage independently. So gone are the days when I have all this storage left over because I'm mostly using my compute, and therefore I'm wasting a lot of storage. Now we only pay for what we use. And then no expensive data centers. This is a huge one. I'm part of our regional availability team. And so being able to roll out these data centers for people without them having to incur that cost on-premise is huge. And then less management. We're able to provide compute and storage for you without all the pain of having to upgrade and do all the management yourself. I think global presence. Hey, I can spin up a data center here in Asia. I can do it in Australia. I can do it in Japan, all over the place. And that's one of the key benefits of being able to run in the cloud. And then last of all, being able to have availability SLAs, being able to be guaranteed, hey, I'm going to have this available for this many nines. So I'm going to talk a lot about compute and storage today. So I wanted to level set everybody and talk about, what am I talking about when I talk about compute and storage? So in compute, I'm mainly talking about the compute layer, which includes things like, Azure Databricks, HDNSite, Azure VMs. From the AWS side, we're talking about EMR and EC2. And from Google, we're talking about Dataproc and GCE. And from the storage side, what I'm going to mainly talk about today is remote storage. So notice I don't list any attached disks or anything like that here. I'm mainly talking about Azure Data Lake or Blob Storage or S3 or Google Cloud Storage. And then on top of this compute layer, what we're going to have is a bunch of different workloads running, right? We're going to have Spark, Hive, MapReduce, Storm, Kafka, you name it, right? All these can run on top of our compute layer. So what are the challenges that we see, right? We've talked a little about why cloud is great and why there's so many benefits, but what are the challenges that we see? So eventual consistency is one of them. Being able to have your data be consistent, that's the problem that we've definitely faced. File semantics might be different than what you're used to. You might only have a subset of APIs instead of what you're currently used to on-prem. And then last of all, and what we're going to really focus on today is the different performance characteristics. We're going to see, hey, on-prem I can see this, but hey, on the cloud I'm actually seeing something different. And why am I seeing that difference? And what can I do to solve that? So we're going to talk about 3 different variants right now. And I'll tell you which one we'll focus on at the very end. The first variant is a CPU-intensive workload. right? And these workloads are mainly characterized by, I'm going to read some data in the beginning, and then I'm going to do a bunch of compute. So maybe I'm doing machine learning or deep learning or maybe natural language processing. And then I'm going to write some data back, which is usually my results. There's also memory-intensive jobs, which use a lot of memory. This could be like PageRank or real-time analytics that need to store a lot of things in memory. And then the I/O-intensive job is what we're going to concentrate on today. This involves things like data prep, or it could be copies. And it's characterized by the 3 phases of, hey, I'm going to write a lot of data, and then I'm going to do some kind of compute. Maybe I'm scanning the data, I'm filtering, I'm sorting, and then I'm going to write a whole bunch of data back. And this is where we're going to see the most benefit from what we talk about today. And so the approach today will be, let's first choose the right infrastructure, right? Without the right infrastructure, we really can't get the performance that we need. Second, we'll talk about how do we use the right yarn settings and being able to set those appropriately to get the best concurrency for our workloads. And then right-sizing the application and making sure the application is utilizing all the capacity and resources that we have available. So let's get into this and talk about the key problem. So this is the key problem that most customers, when they come to me, actually have. So we have compute and we have storage, and we have the network that connects the two. The problem is storage actually gives you a lot of bandwidth, but most of the time when I'm talking to customers, what I see is they're not really pushing and pulling enough data to actually use that bandwidth. So as you see here in the slide, you can see that, hey, I have this huge amount of bandwidth, but I'm only utilizing this small portion of it. And so how do we get to the state where I'm using all of that, right? And this is our ideal case. And this is what we're going to talk about today, different methods to help you be able to use up all that bandwidth. So let's first talk about how a cluster is built, and then on each different level of a cluster, what we can do to tune it to make sure that we get better performance. So the first layer is the physical layer. On top of that, we have the resource management layer. Today, we're going to talk about yarn. And then we have the application layer on top of that. So on the physical layer, what do we see? These are the bare metal. This is like the VMs. These are the machines that we're actually using in our cluster. So this could be the number of VMs. Hey, I have 16 VMs. Or the VM type, which is, hey, I have a memory-intensive SKU, or I have a compute-intensive SKU. I have GPUs in the SKU. That's what I mean when I talk about VM type. And then the size of the VM, right? With the size of the VM, I'm talking about how much memory and how many cores do I have? How much is my network and the size of my NICs? Being able to understand that and optimize for that is going to be super important. And then on the yarn layer, we're going to talk about, hey, yarn can give me a certain number of containers. If I tell yarn I want this many gigabytes per container and this much cores per container. And then they'll give me, hey, here's X number of containers with your specifications. And then the last layer, we're going to talk about the tasks that we tell our application to run. And these tasks are going to be run inside these containers in the yarn layer. And then these containers will be using the memory and the compute that's provided by the physical layer. So that's how all these things connect together. So the first thing we're going to talk about is the physical layer. We'll start easy here. So the easy thing would be, hey, if we increase the number of VMs that you have, great, right? Because what's going to happen is, imagine you have a VM and you have 4 containers that run in this VM. If you have more VMs, now you suddenly have more memory to be able to run more containers, right? And being able to run more containers means you have more concurrency in running your tasks. With 8 containers, I can run twice as many tasks at one time as if I had 4 containers. And so that would be the first and most simplest thing to do. The second thing you can do is, the VM that I'm using really isn't optimized with the right amount of memory that I need. So, maybe instead of choosing this VM type, now I'm going to use a VM that's more memory intensive. It'll give me more memory. I can create more containers, and then I'll be able to run more tasks concurrently. And that's really the key here. We want to run more concurrent tasks. And the last thing is, hey, on the physical layer, we have VMs that have a certain amount of bandwidth. So each NIC can be small or large. And so if we're stuck with using a small NIC and having a small amount of network bandwidth, we're not able to fully leverage everything that the storage layer can give us, right? We're actually going to be, at that point, bottlenecked by network. And so no matter how much storage bandwidth I give you, it doesn't really matter at that point because you're going to be bottlenecked by the network. So use VMs with more network bandwidth. So what is the solution, right? So if we can do some of those things that we just talked about, we're going to be able to get a little bit more of that throughput and be able to use more of that bandwidth that storage is giving us. So the second layer is the yarn layer. So this layer is really cool because, hey, the first thing we can do in yarn is let's use smaller containers, right? And why I say this is because reading and writing really doesn't take that much memory to do. It's not like we're doing anything super compute intensive. So in our containers, we can use smaller containers to do the reads and writes. So let's say I had 4 containers here, and these 4 containers were 6 gigabytes each. Hey, now if I just reduce the size of that container from 6 to 3, now I created 8 containers, and now I can run double as many tasks concurrently. And this is great, right? You can tell your boss, hey, I didn't spend any extra money, but now I can run twice as much. That's great. I mean, that's what I'd love to tell my boss. So this is a good one that you can do without actually spending more money on more VMs. And increasing the cores that you can have per container. So let's say in your container you have 1 core, and now you're adding more cores, and now it's 4 cores per container. You can actually run more tasks in parallel because each core can run a task. And so if you're running 1 task with 1 core, now you can run 4 tasks with 4 cores. So this is just increasing the concurrency that you can run per container. Whereas the previous one is we have more containers, and therefore we can run more concurrent tasks. So with this, what are we going to do? We're going to increase the concurrency so that we can run jobs faster and make the I/O, the read-write phase, a lot shorter. And so, with some of these steps, we'll be able to get closer to using the entire bandwidth. And the last thing is being able to run tasks within these containers. So use all available containers. So we've already talked about how to create more containers, right? Great. If we create a whole bunch of containers but don't actually put tasks in them, we've really defeated ourselves. And so what we want to do is make sure that we have tasks running in all these containers. So if you have large tasks, maybe we break them down to smaller tasks. And therefore, with these smaller tasks, we're going to run, be able to put them in all the containers and be able to run them concurrently. So this is the application layer. And with this, we hope to be able to take up all that bandwidth that storage can give us. And what you see after you've put some of these guidance in practice, you'll see you'll be able to use more of that bandwidth and be able to push more and pull more from your storage. So how do we do this, right? Okay, great. This is good, like guidance knowledge. How do we actually do this in Spark and Hive? So we're going to dive a little bit deeper here. Okay, so first, we're going to talk about Spark, and then second, we'll dive into the Hive application. So let's start with some Spark concepts. So within Spark, we have a cluster, and within the Spark cluster, we have a certain amount of resources, right? We've talked about there's some memory, there's some cores that the cluster gives us. So we're going to have a certain amount of resources in the cluster. Within a Spark cluster, there's going to be a certain number of applications that are running. So here I'm showing 4 concurrent applications are running. And then within each application, they'll be running a certain number of executors within the containers that we provide. And then within each executor, we'll have tasks that are running within these executors. So you might have like 4 cores per executor here, and you'll be able to run that many tasks per executor. So let's talk about like a Spark cluster and give an example here. So in this example, we have a Spark cluster, and we have a default of 4 apps that can run concurrently. And what that means is, hey, maybe my IT administrator feels like I really don't need to be, you know, letting people use all the resources. So I'm going to, by default, split up the cluster and say, your job can use a fourth of that cluster. And so if I had a total resources of 64 cores and 192 gigabytes of memory, your app, let's say your app is a notebook and you're running some of your code in this notebook, your app is going to be using 16 cores and 48 gigabytes of memory. So basically dividing the total amount of resources that we have by 4. So what's really happening here? If nothing else is actually running on this cluster, you're actually underutilizing the cluster. You're not using all the resources that are provided, and so therefore you're leaving some resources on the table that could be utilized and make your job run faster. So first, what we have to do is we have to first determine how many apps are running on my cluster. So maybe you figured out, hey, me and my coworker, we're both running notebooks, and I know that we're going to be running them at the same time. So let's say that we split our cluster in half, and I'll use 32 cores and 96 gigabytes of memory, and he uses the other half. So what we want to do is we want to utilize all the resources and make sure that when we, for our app, we're creating the right number of executors with the right amount of memory per executor and the right number of cores to maximize the usage of our resources here. And so what we can change here is the size and the count of how many executors we have. And so we'll dive a little bit deeper into what that means. So there's going to be some Spark parameters, and some are related to size and some are related to count. Within this size, we have executor-memory. And this basically governs how much memory is each executor going to have. The second parameter is executor-cores. And this governs, at least how many cores will we provide for each executor. Whereas the first one is at least how much memory are we going to provide for each executor. So that helps you set the size of each executor appropriately. And then the last one is how many executors are we going to have, right? What is the number of executors? And so that's the size and that's the count, and we'll talk about how each one of them play well together. So it's setting the executor memory. So here's an example, right? If we had by default 6 gigabytes of memory for each executor, we'll have 16 executors, right? So I'm going to assume my app resources are, in our example before, 32 cores and 96 gigabytes of memory. And so if you divide 96 divided by 6, you'll get 16 executors. So we know that we've talked about, hey, having more executors is good, right? Because I can run more things in parallel. Okay, what do we do? So let's take the 6 gigabytes of memory and reduce it down to 3. And then we can get 32 executors. So we're actually running a lot more in parallel at that time. So we're applying kind of what we learned before. So you might be asking me, Stephen, I want like 1 million executors. Why can't I do that? Yeah, that seems like a great concept, but at some point you're going to get the gnarly error that says, hey, you're out of memory. And at that point, you're like, okay, maybe I can't have 1 million executors. And so I need to step it back up a notch where I was able to run my job successfully without running out of memory. And then you can always go the other way, right? If you need a little bit more memory in your in each executor, you can always increase the amount of memory. But at that point, then you're reducing the amount of executors that you have to run. And one of the tips that we've seen is that we should set the executors to no more than 64 gigabytes of memory. Why we say that is at a certain point, we actually start running into inefficiencies. So adding more memory doesn't really help and starts causing some issues. So now let's get into executor cores, right? So let's say by default, I have 4 executor cores in each executor. So if we divide 32 by 4, we get 8 executors. We can also increase the number of executors that we have by reducing the number of cores per executor, right? So if I wanted more executors, I could reduce the number of cores. So 32 divided by 2 would be 16 executors. And if I went the other way, I could, get fewer executors, but be able to run more concurrent tasks within each executor. So if I had 5 cores, I could create 6 executors. And what's a good practice here? What we've seen is, hey, setting cores between 2 and 5 is actually pretty good practice. because, as I said before, once we get into too much memory or too many cores, we start seeing inefficiencies, and we're not able to process tasks as efficiently. Okay, so how do we wrap this all together, right? It seems like there's like a conflict between, should I set more executors, or should I put more cores inside each of my executors? And so let's tackle that. So let me take an example of, hey, if I tell Yarn to give me 4 cores and 6 gigabytes of memory per executor, what do I get? So if I do the math here, 32 divided by 4, I get 8 executors. And from a memory standpoint, I get 96 divided by 6, which is 16 executors. Great, cool, math is great. But the thing that isn't great is, hey, we can only use 8 executors. And what's happening here is we're actually underutilizing the memory. Right? We have some amount of memory that we're not using because we've just left that on the table because of how many cores we need per executor, or what we've told Yarn to do. So there's some memory that's being underutilized. We don't want that because we want to fully utilize all our resources. The second example is, great, I have 2 cores and 12 gigabytes of memory. What happens there? So now I've kind of swung too far the other way. I've used 2 cores, which is 32 divided by 2, I get 16 executors. And if I do 96 divided by 12 gigabytes of memory, I get 8 executors. And now we're still in the 16 and 8 scenario where we have to take the min of that, and we get 8 executors. Now, instead of being memory underutilized, now we're CPU underutilized. So we don't want that either. So how do we get to that happy sweet spot? So the happy sweet spot here in this example is having 2 cores and 6 gigabytes of memory. Because when you do the math, we get 16 executors for each, for this example. And we're able to actually set 16 executors for num-executors and be able to fully utilize both memory and CPU. So this is our happy place, and we want to, whenever we're doing these calculations, make sure we're utilizing both memory and cores efficiently. So in summary, for Spark, we've talked about how we can make sure that we're utilizing all our resources. First, by understanding how big is our cluster, how many apps are running on our cluster, so we understand what we can use and not be able to, use somebody else's resources. And then once we understand how many resources we have, how do we set memory and cores appropriately to get the right balance of executors and to be able to fully utilize all the resources that we have. And what does this do, right? We get to increase the concurrency that we have, and this increase in concurrency, as I'm going to keep on saying, is going to help you run your jobs faster. And especially in these IO-intensive jobs, we're going to be able to cut down the time of how much time is spent in that portion of the job, which will drastically reduce the time of your job. So now that we've talked about Spark, let's go a little bit into Hive. So Hive is a little bit different, and so we'll talk about some basic concepts of Hive. So there's some source data that we're trying to input, right, and read from storage. And where this happens is we have a map stage where we'll have some mappers, and they'll run inside these containers, and we'll read the data from the storage. And then the next stages would be the reducer stage. So we'll have one or many reducer stages, and within these reducer stages, we're able to do things like sorting, shuffling, computations. And then at the very end, we have the last reducer stage where we're going to be able to do some writes back to disk. Right? And what we're going to concentrate on today for this presentation is we're going to look at the first map stage and the last output stage or reducer stage where we do the reading and writing. So Hive is a little bit different in Spark in that in Hive, each container runs single-threaded. Right? So in each container, I can run one thread, and therefore having more containers is always to my benefit because I can run more threads concurrently. And for example, today we're going to use Tez. And so with Tez, we're going to start with a default of 6 gigabytes, which we have 16 containers. Right? So we know by now, hey, if I reduce the amount of memory, I can get more containers. And this is especially useful because Hive is single-threaded, so the more containers I have, the more I can run concurrently. And the more I can run concurrently, the faster my job can run in an IO-intensive workload. And at the same time, like we talked about before, you'll run out of memory at some point if you go too low. But we do want to try to create as many containers as possible. And how do we do that in Hive? So I'll talk about the case where we're using Ambari. In Ambari, we have a minimum yarn container size. So say, hey, maybe the minimum container size right now that's set in Ambari is 3 gigabytes. And that's usually a good place to start, right? Because there's already a min size. We can set hive.tez.container.size to the same size as the minimum yarn container size. So these are two different, so hive.tez.container.size is something that we can set. And then the minimum yarn container size is something we can set in Ambari. If we want to go even lower than that, that's fine. We can go into Ambari and change the minimum yarn container size. Maybe we want it to be 1.5 gigabytes. So we'll reduce it to that, and then we can set our hive.tez.container size appropriately. We don't recommend going with more containers because at that point, then we're running less in parallel. So we would more like to create more containers, and that's why we have the green on the left-hand side there. So again, as we talk about running tasks and how many tasks we're going to run within these containers, we want to run at least as many tasks as there are containers. Right? So this is for mappers and reducers. When we're in the map stage, we definitely should try to run as many mappers as there are containers. And again, in the reduce stage. And I get a lot of people asking me, why is my reduce stage so slow? I'm stuck at like 80-something% or 90%, and it takes forever to finish. And so a lot of times they're running with very few reducers at that point. And so they're not able to take advantage of the concurrency that we can provide from a storage standpoint. So Tez is actually pretty smart. And so just doing that first thing and setting container sizes to be smaller and be able to run more containers is going to help you a very large majority of the time. And because Tez is pretty smart, they're able to figure out how many map tasks should I have given the amount of containers that I have. At some point, though, we have seen that there are some more advanced tuning techniques that could be used when Tez doesn't set this appropriately. So I'll go into a couple of those, but just know that the first one is probably the main one that you should be looking at. The second two happens in some niche cases, but we'll talk a little bit about that. So let's use an example of I have 5 containers. So what Tez does is, Tez is like, I'm pretty smart, and I think I should run 1.6 waves on a best effort. And what does waves mean, right? So a wave is like, my first wave would be I'm running 5 containers, and I'm running 5 tasks within those containers. And then the second wave would be, hey, I have some more tasks that I need to get done, so I'm going to run another wave of containers. And why they didn't choose 2 and why they didn't choose 1 is because there's going to be some tasks that are going to be running longer than others, right? So we know that maybe in this container they have a longer task. So I'm going to run some shorter tasks in these other containers and be able to, finish at around the same time at 1.6 waves. And this wave thing can actually change a little bit depending on the size of your cluster, but we'll use 1.6 for this example. So understanding that some tasks are longer and some are shorter helps Tez be able to make this kind of judgment call here on best effort. So what happens, right? If we have 5 containers and we use the Tez wave format, we'll get 1.6 times 5 and get 8. Cool, that actually works pretty well. However, let's say that we have an instance where we have 80 megabytes of input data. And each task is actually 10 megabytes large. This is great, but if we actually have a tez.grouping.min size, meaning each mapper or each input task can only be 20 megabytes, what happens there is that, hey, now the best effort wave formula can't be taken into account because Tez is overriding that by having this min size. And so each mapper actually has to be 20 megabytes. And being 20 megabytes gives us 4 tasks. That's a problem, right? Because what have we kind of all learned in the last 20 minutes, 30 minutes? We've learned that we need to use all our containers. So if we have 4 tasks and running 5 containers, we're again underutilizing our resources. So that doesn't sound good, right? So what do we need to do? So let's change that setting. Let's change tez.grouping.min size to 5 megabytes. And when we make it lower, we're able to go back to let Tez do what it does well and use their wave formula to give us 8 tasks again. And so now, since each of these tasks can be 10 megabytes large, and we have a min size of 5 megabytes, this works out again. Tez is happy, we're using all our containers, and we're again having that concurrency to be able to help you run your jobs faster. So the other example is on the reduce side. What can we do on the reduce side? So Tez is, again, pretty smart, and it tries to evaluate how much data needs to be processed at each stage. Remember before we talked about there's a couple stages that could be happening in the reduce stages. So let's say in our example, Tez is estimating that there's 512 megabytes of memory of data that needs to be processed. So it says, okay, I think each reducer should be about 256 megabytes by default. And so that's this parameter here. But I'm also going to have this extra factor of 2, where I'm going to multiply it by 2 so that I can get more reducers. And so what happens here if we do this calculation? 512 megabytes divided by 256 megabytes, we're able to get 2 times 2 equals 4. So we have 4 tasks, 5 containers. I'm sure we can all say this together. Hey, we don't have enough tasks to run in our containers. So what should we do? We need more tasks, right? How do we increase the number of tasks? So we should just set this reducer size to be smaller, right? So if it's 256 megabytes, let's set it to 128. And how does that change our equation? So if we divide 512 by 128 times 2, now we have 8 tasks. And with these 8 tasks, now we're able to saturate and use all our containers, and we're going to be able to better use the resources that we have. So in summary, for Hive, the main thing that we want to do is take a look at the container size. And that's going to be the overarching thing that we can do in Hive, because more containers on a single-threaded system will give you more concurrency if you create more containers. So decrease the amount of memory that's in each container, and then you'll get more containers. Second, if you need to do some more advanced tuning, you're thinking, hey, I'm still not getting the right performance that I need. I want to do a little bit more. And so I would investigate a couple of these parameters, seeing if the min size of the Tez grouping is too large, then make it smaller so that you can run more tasks within your containers. And the last one is, hey, if my reducer size is too big, maybe I'm not getting enough reducers at that point. And so therefore, if I'm getting more reducers, I can run more in parallel by reducing the size of each reducer. And so in summary for Hive, we want to run more things in concurrently, just like we've said before. And the more we can run concurrently, we're able to utilize all that storage throughput. So what are the key takeaways here? We need to maximize usage of the throughput, right? We know that we have this huge straw that we've been given. So for example, if you're actually really thirsty and you're trying to drink from this straw, you wouldn't be drinking it slowly, right? And letting only some water through. You're going to be trying to drink as fast as you can so that you can get as much water as possible. Similar concept here. To reiterate, we want to use up all the bandwidth and all that straw space that we have to be able to get as much reads and writes from storage as possible. And how do we do that? We need to choose the right cluster. So and this is a very common example actually. I see a lot of people talking to me about, hey, it's really slow. And they're trying to use this really tiny cluster and trying to read terabytes of data. You can't really use 4 nodes to read terabytes of data and expect a lot of good performance there. So number one, choose the right cluster size. I would say that's really important. And then second, apply the right yarn settings. Being able to just set memory and set cores appropriately so that you maximize the amount of containers that you have will definitely help you with concurrency and push as much data through in parallel as possible. And then last, right, making sure your application is the right size, making sure that you have tasks that are running within these containers, because you could have done all the right things by setting the right yarn settings, but if you didn't, actually use those containers, then all is for naught, right? So make sure you use those containers and right size your application. My name is Stephen Wu. Thank you for attending. Happy to take some Q&A. Yes. Yeah, it's very possible that your cluster's, small in terms of not being able to push as much concurrency through, right? Are you seeing?
For a cluster is already underutilized.
Okay.
And we can process the finish job very quick, and then Spark step EDL storage.
It's still doing I/O. You're saying it's kind of stuck there. Okay. I mean, there could be a variety of factors. Maybe we can dive into your individual use case. I'll be happy to stay afterwards to just talk about what's happening there and what you're seeing. So, yeah, let me take that offline. Yeah. Yeah, I mean, and that's a really good question, right? I mean, you might be running many different workloads. So for Spark and Hive, we've kind of seen how to do that. And I would say for those workloads, you kind of have to understand how much, what exactly workload am I using? How much of the how many applications are actually running, right? Maybe I'm using this much for Hive and this much for Spark, and really understanding what's running concurrently at the same time, because maybe they're not all running concurrently, and at some points we're underutilizing the cluster. So being able to better understand, am I running, my Kafka workloads at the same time as my Hive workloads, and when can I make sure that I'm fully utilizing the cluster and following these kind of principles is going to help, right? It's kind of being able to better understand what's running at the same time, because if I don't understand that, I'm not going to be able to tune things properly. And yeah, it'll just kind of help you understand where to go from there at that point.
Switching to a DataWorks or something, give you an isolated approach?
Yeah, using Azure Databricks, I mean, then you're only running one workload, right? And you kind of know at that point, okay, I'm running this one workload. I know, my IT administrator says I have this much memory. I'm split into this many apps that I can run, by default, and I'll be able to have this much memory and cores, right? And so at that point, you're better able to see what's running at the same time and be able to better tune it. Yeah.
Is there a way to set the parameters that's independent of the available resources?
Independent of what?
Available resources.
So whenever you set any of these parameters, you're going to override the existing default, right? So if you have a default that's been set by your IT administrators, if you're setting these manually, you're going to override that.
Now, what if you have a Spark job and you want to choose a right cluster?
Mm-hmm.
So how do you do that? How do you set number of executors, like how much memory the cluster wants? How do you come up with that?
Yeah. So first, you have to understand, how many resources you have, right? Are you asking about if I know how many resources I have, or how many should I procure?
Yeah, how many should I procure?
Yeah, I mean, so you kind of think about, hey, if I'm running this job and it's kind of slow, let's see if the bottleneck is I don't have enough VMs, right? So add some VMs, give yourself a little bit more memory, increase the number of containers and cores that you have, and see if that actually helps your job, right? If that's the bottleneck, then great, right? You've added a little more VMs. Maybe you can keep on increasing that. But maybe you're looking at that and it's not really doing anything, and you're saying, maybe I'm not bottlenecked by that. Maybe I'm bottlenecked by network or something different. So it's kind of like trial and error here. It's hard for me to just give you hey, you should do this and it'll work, because you got to try a lot of different things. And so that's kind of what I would advise. Yeah, tweaking things here and there. Sorry, Joe.
I have a question on, obviously any VM has a ratio of the cores to memory.
Yes.
If you have a fully utilized yarn configuration for a VM,
Mm-hmm.
yet you find your CPU utilization on the VM is still low,
Mm-hmm.
have you used virtual cores to offset that?
Yeah.
What do you think? Because I know the default is 1-to-1.
Yeah.
Curious, is there any performance impact by increasing the virtual cores?
Yeah, and we've tried that before where, hey, if I increase the virtual cores, does it give me a difference? I mean, it's kind of hard to have a one one size fits all answer, especially in performance tuning. Maybe we can dive into your case to see exactly, what you're doing. I'll be happy to kind of hear what you guys are doing and see if I can help there. Yeah. Okay. Okay. I'll take any questions afterwards. I'll be here for as long as you need.